Hey everyone, and welcome. We're about to tackle a math problem that seems super simple on the surface, but it actually hides this really cool secret about how computers think. You know, it's kind of like a chain reaction, a set of falling dominoes hiding in plain sight.
All right, so here's our mystery problem, 100,000 minus 1, and it's all in binary. Now, if this were just regular, everyday math, you know exactly what to do, right? You just borrow from the left and keep borrowing. But how in the world does that work here when the only digits you got are 0 and 1?
And then you see the answer, a neat little row of ones. It just looks wrong, doesn't it? I mean, how does subtracting 1 from a number that starts with 1 make that 1 just vanish and get replaced by all these other ones? Well, that is the puzzle we are going to solve together step by step. To crack this, we really only need to get our heads around one single fundamental difference between the math we do every day and the math that's powering all of our devices. It all, and I mean all of it, comes down to what happens when you borrow.
Here it is. This is the core secret. In our normal base 10 system, every column is 10 times bigger than the one to its right. So when you borrow, you're borrowing a 10. But in binary, which is base 2, every column is only twice as big, and that means when you borrow, you're always borrowing a value of 2.
Let's actually put a name on that, the binary borrow. So when you grab a 1 from a column over on the left, you're not just adding 1 to your current spot, you're adding 10 in binary, which is the number 2. And just understanding that one little shift is honestly the key to everything else.
Okay, so the good news is once you get that borrowing rule, the rest of binary subtraction is actually incredibly simple. I mean, there are only 4 things that can possibly happen in any given column.
And as you can see, it's pretty darn straightforward. 0 minus 0, that's 0. 1 minus 0, still 1. 1 minus 1, back to 0. So yeah, 3 of the 4 rules are completely what you'd expect. It's only that last one, 0 minus 1, where things get interesting. That's our special case.
So yeah, let's really focus on that one. That last rule, 0 minus 1, that is where all the magic happens. It's the one thing that forces us to borrow, and it's the trigger for that whole domino effect that's going to solve our opening puzzle. So now that we're armed with this new understanding of borrowing, let's circle all the way back to that problem from the beginning. We are finally ready to take on the long-distance borrow and see exactly how it all plays out.
Here it is again, 1 followed by 5 zeros, minus 1. Okay, so starting from the far right column, we immediately hit our problem case, 0 minus 1. We have to borrow.
Right off the bat, we need to borrow, but the column next to us is a 0, and the next one is a 0, and the next. So we have to go all the way to that lonely one on the far left to start the borrow. And this is it. This is where the domino effect kicks in. As that borrowed value travels all the way back to the right, every single 0 it passes through flips to a 1. It's like the value is being handed down the line until it finally delivers a value of 2 to the column that needed it, letting us solve the problem. And there you have it. The 1 on the far left became a 0, all those zeros in the middle flip to become 1s, and our final column is 1. The mystery is solved, 0, 1, 1, 1, 1, 2. It's just a chain reaction, all started by one single borrow. And this chain of ones, it isn't just a neat trick, it's the why behind the whole thing. It's this beautiful picture of how place value actually works in base 2. Think about it. That far left 1 in our problem, it was worth 32. When we borrowed from it, we basically gave 16 to the next column. And that column gave 8 to the one after that, then 4, then 2, until the final column got the value it needed. The ones that are left behind, they're just the proof of that journey. That's the domino effect in action. So that's how you do it by hand. But what's really fascinating is that computers, the things that live and breathe binary, they often use a really clever shortcut to avoid this whole borrowing mess completely. I know, it sounds totally impossible, right? But this is genuinely one of the most elegant tricks in all of computer science. What if you could get the exact same answer to a subtraction problem, but by only using addition?
This method is called 2's complement, and it's basically a way to represent negative numbers in binary. The process is pretty simple. You take the number you want to subtract, you flip all its bits, so every 0 becomes a 1 and every 1 becomes a 0, and then you just add 1. That creates its negative version. So now instead of subtracting, you just add this new number. And this is so incredibly efficient because it means a computer's processor doesn't need separate circuits for adding and subtracting. One piece of hardware can do both jobs.
So the really crucial point here is this.
While we learn the long borrow method to understand the principles behind it, computers have totally optimized the process. They found this elegant, super efficient workaround that simplifies their own internal logic and, of course, makes them faster.
All right, so what are the big takeaways from all this? First, just remember that in binary, borrowing isn't about 10, it's all about 2. Second, when you have to borrow across a bunch of zeros, you create that really cool chain of ones. And finally, don't forget that clever trick computers use. They often cheat by turning subtraction problems into addition problems using something called 2's complements.
And that kind of leaves us with one final thought. If something as basic as subtraction can be so cleverly flipped into its opposite, what other brilliant shortcuts and elegant solutions are hiding just beneath the surface of the technology we use every single day?